I've started recording and sharing my screen. Yeah, is the screen visible to all?
Yes, sir.
Okay. So we were discussing about ensemble techniques. So basically, what we started off with is to denote what is the binary classification. So we started off with just simplifying the problem with binary classifier. So as you know that binary classifiers are classifiers where the hypothesis is a function from the input space to either z plus 1 or minus 1. That means whether we are taking lectures in online mode or live mode. So there is not the case that it's an alphabet A, B, C up to Z. There are 26 opportunities. This is not the case. Here the case is something is yes or no. That's a binary classification. And also in the last class, we have seen that the whole role of learning is to minimize the in-sample error, as we have already know, since the in-sample error tracks the out-of-sample error. So effectively, the error, if we normalize it, it's within a range 0 to 1, considering the probability of error. So this is a coin flip. If you only use a random coin flip to go with your hypothesis, your error will be 0.5 in that case. However, we say that a classifier is a strong classifier is if you reach somewhere here. So this is your strong classifier if your error is somewhere here. So this is we denote as error. And on the other hand, as in the last class, we have seen that sometimes we reach this point of situations where we call it something as a weak classifier. And the whole goal of ensemble learning is to first create a set of weak classifiers, and then among those all set of weak classifiers, take a vote and therefore create a hypothesis H. So with after the vote, if a hypothesis H is created, and so that we can say that this is a strong classifier we get finally. So that is the whole process which we called. So this is the process which process we call ensembling or ensemble learning. Now, why we thought about such kind of a process is that though our classifier is weak, but suppose in this space, suppose we talk about three kind of a weak classifier. Suppose this is the three classifier points where it goes wrong. So this is my total space, and I say that these are the points where the first classifier H1 is wrong. This is the space where H2, the second classifier, is wrong. And this be the space of points where H3, my third classifier, is wrong. Now see if yeah. So am I audible or it is just cutting down a little?
Yes, sir.
Yes.
Audible.
Yeah, am I audible properly now?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Perfectly audible.
Okay. So the thing is that if we could get such kind of an independence, then our ensembling will be very strong. Vis-a-vis, we also have seen a scenario where, let's say I got this kind of classifiers where these are the errors that they produce. Now see, I am taking a vote. Suppose I have three classifiers, so I am taking a vote, meaning that my final classifier on X will perform just as a sign of the first classifier performance plus the second classifier performance plus the third classifier performance. What does it mean? Since each of them can take a plus or a minus, binary classifier, plus or a minus, plus or a minus, this means that if two of them agree, the output will be with respect to any two of them that agrees, right? Because if two of them are plus, even if one of them doesn't agree, my sign will be plus. That's it, because it's a plus one or minus one. Now, The challenge comes is that since these are the erroneous positions where two of the hypotheses, so again, this is where H1 is wrong, this is where H2 becomes wrong, and this is where H3 becomes wrong. So these shaded regions are the bad regions where in that point both of the classifiers are wrong. So this kind of a voting will be problematic in this case. If both are wrong, then the wrong output, wrong sense of classification will happen in ensembling. So one thing is that how can we reduce such kind of dependencies between the classifier is the only target of ensembling, because if we could reduce that, then my ensembling method ultimately will be strong. So in more formal way, in this diagram, the orange color portion, the more the orange color portion is, the bad is my ensembling. So we need to have a trade-off that the area covered by this orange color should not be more than any one of these. Then simply we may argue that we will take that one, throwing out this ensemble technique. Okay, are you getting me why we are going for the independence in ensembling? So in the last class, we
Yes,
have
sir.
a very informal way of specifying the independence. Today we will see the more formal notion of it. So first of all, let us try to see the informal thing to start with. We have a set of data. Now it's a supervised learning. That means our data are x1, y1. These are labeled. So xn, yn are my data points given. So what we are doing is that with respect to these data, I just create a first sample data set. And then with respect to that, I get my first classifier. So remember, this is a subset of all the endpoints. I just picked up by some probability value and then create a data set. Initially, all the probability values, I keep the weights of all of them are same. So these are W1 up to Wn, and initially, that is initial phase, all of the weights are same 1 by n. So this data set is created by a subset of it. Then what I do is that I will try to check some kind of problems that happen through H1. Since H1 is a weak classifier, so some of them will not be classified well. So then what I would do, I take the same data, I make some exaggeration upon this data. What does this exaggeration? As we told that the wrong points, I will try to increase the probability of the wrong points, and the right points, I will try to decrease the probability. And therefore, with that new set of probability, informally, I am speaking, I will take another, create another data set, and that data set will give me another classifier. Third case, again, I will do this experiment. So this exaggeration is basically where H1 is wrong. I put those weights on those points to be pushing higher. The third thing that we could do after this is that again we will start another exaggeration. So here the exaggeration will mean that H1 and H2 differs. Because see, I will be taking finally this one to vote. I will be taking this one to vote. So where H1 and H2 differs, there H3 is very much matter, because if they differs, one should be right and one should be wrong. Then H3 choice is very much, I mean, is of utmost important. And therefore, where these two will differ, I will exaggerate those points with respect to increasing the probability or decreasing the probability. And then again, I sample and create a new data set and then create another. So finally, all of these, I will keep on doing this sometime. Then finally, you see the final hypothesis that you will get. What I want to reach is that, first of all, I have to take a sign that is the voting of all them. So I have H1 of X, I have H2 of X, I have H3 of X. Obviously, I go on voting the binary classification, so I will add them. Now, instead of adding them as it is, I also associate some weights alpha 1, alpha 2, alpha 3 weighted. So what I will do, I will just not add the points directly, but I will have some kind of, in English, we call it as weighted wisdom of expert crowds. So from this, we pick up one of the expert crowd and then have a weighted wisdom of it. And finally, the average, or rather the majority, I will not say average, the majority of the weighted wisdom of average crowd is this one. Agreed? The philosophy, now we will go to mathematical details, what we will be doing. Right?
Yes, sir.
Yes or no? So therefore, you see now my parameters that need to be in this iterative process that need to be done is that whenever you choose a H1 with respect to these points, your error should be reduced. And depending on that, at each iteration, you need to choose this weight, because at each iteration T, this weight gets changed. Initially, it is 1 by n. Then something classifies good, something classifies misclassifies. Depending on that, I will have an exaggeration. Exaggeration means changing the weight of every point so that I pick up those points from the next type of hypothesis building. So this is one of the things that I need to see from an algorithm and mathematical perspective. The other thing that I need to also see is what are these alphas. These are my free floating parameters. Right? So these two I need to determine in order to complete this algorithm and find the ensemble. Agreed? Up to this point?
Yes, sir.
Sir, excuse me, sir. We build H3. I mean, we give more weight to those points in H3 where H1 and H2 differs, right?
Yes.
Is it?
Yes.
I mean, it is like H1 is. I mean, either of H1 or H2 is making mistake. It is like that. Or...
Yes, definitely, because if they differ, then it's a binary classification. So if some point it's a plus and this one's a minus, then one of them should be correct, right?
Yes, sir.
Isn't it? So that means my H3 right now is very crucial in those points. So building H3 is very crucial in those points. So in this data set, I want those points to must participate. So
okay,
that
okay, I got. I like. Is it like, sir, H3? Okay, okay. Is it like, sir, H3 would
IPL elimination, you get 2-3 chances.
Okay,
right?
Okay, sir.
Somebody loses, but he is the top of the group. I get him another chance to see through another weak classifier whether he is classified well. Right? So then we aggregate.
Yes, sir.
Yes, sir. Thank you. In this process, the weights of either the hypothesis and the points, these are our important parameters to understand, or to by algorithmically we need to compute.
Sir, can you explain the where you are creating the data with exaggeration, that part? Means
I will explain it exactly mathematically. So exaggeration means if you take a subset of the data and create a hypothesis, since it's a weak learner, some data will be correctly classified, some data will be wrongly classified.
Yes.
We increase the probability of choosing in D2 those wrongly classified points more than the correctly classified by H1. That is the exaggeration of those probability of these data points.
Okay.
Okay. That's why how we are proceeding. So this algorithm that we will discuss is called AdaBoost. And if you have gone through a machine learning course, you must know AdaBoost, because this is such a fundamental algorithm. This gives the Ron Sapphire a Gödel Prize, which is a prize for a best paper over the last decade. So there are every year some people gets a Gödel Prize. If you search it, you will get it. It's a most coveted research prize in computer science, one of the most coveted research paper oriented prize, that this paper is one of the best papers in the decade, or maybe last 5 years or so, like that. So it was in 1997 paper they proposed this technique of ensembling through adaptive boosting. So let us try to go into the math slowly. I mean, I will try to make it as lucid as I can. Okay, so first of all, what kind of weak classifier we think of? I mean, since we are saying that we will take a weak classifier, let us take a decision tree model, rather a very naive decision tree model, which is obviously when I tell you, you will see that yes, this will be weak. Suppose I have these points. Now I call my classifier as decision tree stumps. Decision tree stumps. It means that it will just put trying to find a line either in this direction or maybe in this direction with only one attribute. There are two attributes, with only one attribute I will classify. Everything in this side will be one class, everything in this side will be one class. Or everything in this side will be one class, everything in this side will be other class. How many such decision stumps can be possible if there are 3 points? Different decision stumps.
6.
In one direction, 12 in other, right? 6 in one side. Because if you see, if this yellow line is put, all of the right point I can by hypothesis can tell plus, all of the left as minus, and vice versa. So per decision point, two outcomes can be possible. Now my decision, these stumps can be here, the stumps can be here. Now if I take the rightmost one, then all the left point could be plus, right point could be minus, and all the left point could be minus and the right point could be plus. Whereas if I also take this one, then this and this are same. So therefore 3 into 2 in each direction, so total 12. So rather 2n number of decision stumps we need to consider, or 2n number of new hypotheses or new weak classifiers. So we will go by this simple one. It's a very weak classifier, as you can easily understand. I just put in one barrier, and that must have to be weak because it has no basis of generalizing and all. So,
sir, can you explain again how 12 stumps will be there?
how
the answer is 12?
Just tell me how many ways you can separate this. You tell me how many ways you can build a classifier with respect to these three. Suppose I build a classifier which separates is this one. So all in this side will be positive, all in this side will be negative is my one classifier, or all in this side is negative, all in this side is positive is another classifier. So each stump can create two classifiers, right?
Okay, sir, I got it.
So
Yes, sir.
I can put it here, I can put it here. 3 into 2, 6, both side 12. Agreed?
Yes, sir.
Okay.
Yes, sir.
Okay, so now let us start the algorithm. So therefore, as I said, that my final goal is to get such kind of a thing where I can aggregate the wisdom of experts. This is not square. I am saying this is a hypothesis. So which means that you can apply such kind of a hypothesis building in a recursive manner, because as you can see, you are aggregating h1x, h2x, h3x. While aggregating, it can also recursively call that set of decision space and can grade it. So if my hypothesis is simple, I can have recursive formulation or something, anything like that. So recursive formulation means at any htx, basically you have ht minus 1x plus alpha t htx. Yeah, kindly mute yourself, whoever is unmuted. So therefore, this is what by the recursion I want to mean, that I could compute. So at each step, I just take a h1x, exaggerate the data, get an h2, exaggerate the data over with respect to both, get an h3, exaggerate the data with respect to the results from all three hypotheses, get the fourth one. So this is the recursive formulation. I hope if you understand the exaggeration, you can understand the recursively building the final hypothesis. Now the weights and all the parameters. So effectively what we did is, when we started off, each point has weight similar. Okay, that is for all I. This is from point 1 to n. Any point has the same weight. Now, what is the error that we make at any particular time step? Suppose I start with time step 1. What is the error that I make? it will be the sum of all the weights at time 1 which are wrong. Okay, that's the error, because it's a binary classification. Either you do +1 making a wrong or -1 making a wrong. Since I mean it's +1 or -1, I can just add up how many points that are wrong. So in this case, it is summation of 1 by n. So if we go by generically, if we go by in a generic sense, what we do is that at any step t, the error that we make, wrong meaning my hypothesis of x is not matching with my label, I have this as my error, right? And you can see that since I have normalized it, which means that actually my average error is sum over all points of my weights. And to get it normalized, we also assume that the sum over all weights at any particular time step sums to 1. So which means that this term vanishes, which means this term is 1 and this vanishes. Agreed? So I'm just saying that after a particular step, I get some hypothesis. How many points are, so these may be the labels. So I am saying this is correct, this may be wrong, this may be wrong, this may be wrong, this is correct, this may be wrong, this is correct. Then with respect to that, so therefore I am making error here, I am making error here, I am making error here, I am making error here. So I just sum up the weights to make the total error that I am making after I build hypothesis at time t. Agreed? This is what it's simple formula, and I am normalizing it, assuming my weight is just a probability whose sum is 1. Simple. Okay, but remember this formula. This error is over all the wrong, I sum the weights. Okay. Now this is how the algorithm proceeds. Step 1 of the algorithm says to initialize all weights to 1 by n. This is step 1. Then what I will do, so from this step it will, so this is step 1 or the initialization. Then I will have an iterative version of updating wt and alpha t that you can understand from the previous slide discussion. So first I will try to pick a tth hypothesis, good one, which is weak, but that minimizes my error at that point. Then based on that, I will try to pick what will be my alpha. And depending on that also, I will try to update w at t+1 for each weights. And then again, I repeat. So this is the AdaBoost algorithm is this much only. I mean, I am just mathematically, I will now follow all this. This is the step that we do. With respect to the weights, I create a data point dt. From that, I pick a hypothesis such that my error is minimized. I just, from this, how I will show you each of this step, how it can be done. I will pick an alpha t such that it minimizes the error as well when composing with respect to each of the h's. Then I will update the weight by a rule and do this, go on doing this t number of times. I mean, the number of times or the number of hypotheses that I have in decision terms with 3 points, I will do it 12 times at max because I have 12 different hypotheses. This is the AdaBoost algorithm to be very simple manner, not as simple as in the previous page where we only said English language wise. This is some kind of flowchart wise. Now, mathematical wise, this is one of the good things that we need to always remember, that my error at step is the weighted sum of the wrong things. Now, suddenly the major contribution of Sapphire is to formulate this error in terms of an exponential loss function. And in an interview, he said that how did he formulate exponential loss function in terms of an error? He said that in every Saturday he was trying with each and other different kind of possibilities, and finally cracked in one. And he funnily said that in order to save their marriage, he has to do it. So he he picked this one as an update function. So whatever be my weight at time t plus 1, I have an expected loss, this into y of x, which is not with respect to t, but the value of the point given x comma y. Y is that value of x. And since this is sum has to be 1 to normalize it, we put a normalization factor because the sum of the weight should go to 1. Now see why does this kind of a weight updation rule make sense? First of all, try to look at these two terms. So when it is wrong and when it is correct, can you tell me what will happen when it is correct? Either this will say +1, this will also say, my hypothesis will also say +1. So the sign will be plus, isn't it? Or my hypothesis says -1, the actual data also says label as -1, the sign will be plus. So for the correct case, the sign is always positive. Similarly, if you understood that, for the wrong case, your sign will always be negative. Agreed?
Yes, sir.
Which means, now see the beauty of this updation, we want to exaggerate those points which are making error in the tth time step. Now, if I have a wrong classification of those points, which means it will be e to the power positive alpha t, isn't it? For wrong cases, whatever I have this in t, it will be e to the power alpha. Right? Because for wrong cases, this will be -1. This -1 cancels with this minus, making it plus. That means it is obviously more than whatever I have in my weights, right? Whatever I have earlier, it is obviously more. Rather, the other way, this way. I told right, but the inequality I gave wrong. Because E is 2 point something, it is obviously be more than what I have. So I exaggerate those points which are wrongly classified. Whereas for the correctly classified point, you can see that t plus 1th weight will be. So I divide by e to the power alpha t, because minus sign will keep, because both of them agrees in their sign, making the product as positive. So this is the weight updation or exaggeration that we want to mean. Agreed? At each step, we update these weights.
Yes.
Sir,
Yes.
Sir, why are we going with exponential function?
That's
We
what I.
could have written WIT 1 minus alpha t htx yx. Instead of exponential, we.
No, just let me complete the whole exploration where this exponential. So that's why I told her. I mean that saves their marriage, because otherwise his wife is continuously asking what we are doing the whole Saturday only to find an exponential function. But I will show you that what efficiency does it bring to the whole computation. Okay, and I will show you some of the open problems from this point onwards. I mean, which will answer your question.
So is the reason? Yes.
Yeah, just wait a bit, because I mean, if you agree that this is one kind of a function that we could estimate, just wait a bit. I mean, you
Yes,
can
sir.
get some other functions as well for the loss, but exponential loss is one of the options that Sapphire took.
So, but are we using this because it will converge faster?
I will tell you. Absolutely. Your one point is this. There
Yes,
are two,
sir.
three other points.
Yes.
Okay. So with this weight updation, now I need to see, now what I did is that I can choose an alpha, I can update weight, but with respect to HT, so this part I have done here, I have to also do this part. So how do I pick up an alpha t? What I did was that, let's say, what is my error at time t? It is nothing but each of the point that is responsible for making the error, that is the wrong point sets, into whatever error I get with respect to the points that was given to me as wrong. Now, in order to make this alpha t so as to minimize the error, you know the mathematical trick. It's nothing but del E by del alpha t should be 0. Now, if you differentiate this one with respect to del alpha t, then what will come? So if I generically do it, so over all points, what is the error I am making? Then it is basically, so let me take a bigger space here. So it is basically I was doing, so this sum is nothing but sum over wrong points, wit e to the power. If they are wrong, so that means this will be minus 1 alpha t, plus sum over all correct points. If they are correct, that means they are sign agree. So this will be wt e to the power minus alpha t. So that is actually my E at time step t. Now, if I do this one, I get, what is the differentiation? If you do this one, you will get a differentiation of e to the power alpha t with respect to alpha t into sum over all the wrong points wi t. Here it is not, it doesn't depend on alpha t, so I can do this. This will be minus e to the power minus alpha t sum over all correct points wit equal to 0 due to this. Now, which gives me, now, does it rings a bell of the alpha t? Yes. I can say my alpha t is equal to, if you go into that side, take a log. So let me do not step jump it, because otherwise I will be in trouble. So just take a log of it. So what does it mean? Alpha t ln summation of wrong points wit equal to alpha t. This will be plus, this will be plus, minus alpha t. So putting it this side and taking a log ln summation of correct points wit, which will imply alpha t is equal to half, because this will come this side as 2. So if you go by this side, it is half ln summation of correct point wit by summation of wrong point wit. Am I right in this derivation? So what is summation of correct wit? Remember, epsilon t was summation of wrong wits. Yes or no? So that means this
Yes,
is
sir.
1 minus epsilon t, because summation of wrong and summation of correct gives you 1, all points, right? So this is 1 minus epsilon t. This is epsilon t. Okay. So therefore, they suggested, Sapphire, this is a big proof that they got. They suggested you pick at time step your alpha t to be this one. Okay, so that means whatever your htx will be, that you are going to do with respect to the sign of the previous step t minus 1, you have this hypothesis. Now you are ensembling with tth step alpha htx. So your alpha t, you should pick this. So two things we sealed. We sealed that with respect to tth wi, how can we compute t plus 1th I, which is basically with respect to exponential loss. He has a formula for it. And depending on that, if I have to minimize error, what will be my alpha t to pick up? Or rather here, I could say alpha t plus 1. At the next step, what will be my alpha t to pick up? Now, what does these two frame together? So if these two, I try to write it as 1, 2. One is the updation of the weight at step t plus 1, which was basically the weight at step t. I have to normalize it since sum becomes 1. This is alpha t htx y of x. And the second thing I got, that my alpha t should be half ln 1 minus error by this. Now, if I combine these and these equations together, I get the following. It means that Wit plus 1 is equal to Wit by Z. There are two conditions. If I correctly classify a point, if I wrongly classify a point. What if I correctly classify a point? That means this is to be plus 1. So I have e to the power minus alpha t, where alpha t is this one. So what it will come? Half comes as root minus flips the position. So this will be this. The other one will be e to the power plus t, and obviously you can understand this is a simple algebraic chocolate. Agreed? This will be my Wi if I have this alpha t to be sealed. Right? Calculation wise, yes or no? Now another condition I should not forget. For all I equal to 1 to n, Wit plus 1 is equal to 1. Right? Because that is my assumption of the weight. That's why I normalized and make a Wit plus 1. If I go into here, it means sum over all points means sum over the points which are correct, sum over the points which are wrong at t plus 1 step. So therefore, if I sum over all the correct points, Wit by Z root over epsilon t by 1 minus epsilon t, plus if I sum over all the wrong points, Wit by Z root over 1 minus epsilon t by epsilon t should be equal to 1. Yes or no? Due to this, right? Correct
Yes.
point plus the wrong point sum should be 1. Now I can from here I can easily write this is not dependent on the point anymore. So I can take this out. I can sum of a correct point. I can have only Wit here, plus again this is not dependent on points. Then I can have sum over wrong points. I can have Wit here equal to Z, because Z I can just multiply in all the sides, which means Z equal to, let me see what I get. You know what is this? All correct points, all wrong points weight is, isn't it? That was our formula. That was our formula, right? This is for correct point, this is for wrong point.
Yes, sir.
Then Z is, this is multiplied with this, make it root over this into this. This is multiplied with all this, make it root over this into this 2 times. Okay? Agreed?
Yes, sir.
This makes
Yes,
life
sir.
much simpler, isn't it? This makes life much simpler. Meaning that so where Sapphire left their paper is up to this much. Sapphire left their paper is up to this much. But then some statistician, I forgot the name, he came up and saw a very interesting derivations of Z and then plugging back Z here, which means that if you plug back Z here and take the sum over all correct points, you will get exactly that sum is half. You see, you plug over this in Z, multiply with this, what will happen? Epsilon by t will cancel, right? And in the bottom, you will get 2 into 1 minus epsilon by t. Are you getting it? If I take a sum of all the correct points and sum of all the wrong points. Just do it,
Yes, sir.
in your notebook. Not everything I will do. Do it in your notebook. Make it 2 here. Sum over all the correct points and sum over all the wrong points. So what I want to mean is that if you do this computation, sum over Wt plus 1i, all correct points, and sum Wt plus 1i, all the wrong points, you will see that due to this particular derivation that we can get now, if you do this, exactly it will be half. Yes or no? Getting it? because this is sum over this of correct points. What is correct point? 1 minus epsilon t. This is 2 into epsilon t root over epsilon t into 1 minus epsilon t. So in the denominator only 1 minus epsilon t remains and 2 remains. Here the summation due to this formula 1 minus epsilon t comes over correct point. 1 minus epsilon t cancels and you get this. Agreed?
Yes, sir.
Yes.
And you get this. Agreed? So that was a drastic innovation, because now see, what do we want to be in that whatever way you change the weight, the exaggeration would be such that the wrong points weighted sum should be half. Did you get it? I mean, where is the simplicity now came from? See, gradually let us see again. We started off here. I mean, we have no clue what is the alpha and w. Then suddenly we started off with an exponential loss function. And one of your friends suggested one of the fundamental thing to do it, because exponential loss function decays very fast. In the axis, it decays very fast. So it will be easily converging very fast. Then we thought about, well, it's a good idea. Now let's see how can we make the alpha with respect to minimizing the air loss. We get a value of alpha. Obviously, we get a value of alpha, which is very nice. But still, it is not so nice. It's a logarithm, computationally heavy and all that. Then finally, when we plug in, we get a nice equation. And then at this point, then the AdaBoost algorithm originator, Rob Safire, stopped his paper, said that this is my algorithm, which will update my weight in a very simple way, not in a very cryptic way that I started with an exponential loss function, but we'll do this. For every iteration, for the correct points that it classifies, it will update the weight for the next iteration like this. And for the wrong points, it will update the weight in like this. But some statisticians showed that, you remember that for your normalization, this factor is always 1. That means your normalization factor is this, which means the way you update all the correct points and the wrong points, their sum should be half. Makes the life much more simpler, that the probability of updation in both sides should be equal. If you downgrade something, you have to upgrade in the other way, right? And make your set. The only small things that I remain in this algorithm is about this decision stumps. How can we efficiently compute it? Because we need to compute 2n number of hypotheses. So obviously this will be 2n number of steps we have to go. Can we reduce it? So if you look closely, that a simple algorithm like decision stumps also has some redundancy. Why? Let us see. I have plus, plus, minus, 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 plus, minus, plus, like that. Now see, I want to get classifiers which are different, right? So is this and this classifier is at all produce a different outcome? If you take this classifier, either this side is plus or minus and the opposite side is minus or plus, which will eventually, for this point, it will eventually either classify at this point or misclassifies this point. Whereas this one also, even this one also, all these are not good classifiers. You can take any one of them, that will do, isn't it? So these are all bad redundant combinations of classified stumps. Because if you go right side, one side further, then one of the classification will give you one more point wrong. So these are redundant. Yes or no?
Yes, sir. Yes.
So that means I do not have to, so some kind of VC dimension now comes in. I do not have to enumerate all types of classifiers, weak classifiers that I can get to it, because these two classifiers, all of these ranged classifiers have bigger redundancy in them. So I want these to be independent, right? The whole goal of these all to be independent. Now, if I take this and this and this, there is a chance of dependency, and therefore there is a bigger chance of sharing the error space, which is dangerous for me. So these will be my bad guys. I will not take all of them, but just take one of them. So though in the worst case, as we claim, we have 2n number of stumps for n number of points in 2 dimensions, for d dimensions, for n number of points, as you can understand, we have dn number of stumps, but it is practically much less because we have redundant stumps which sacrifice the independence factor. So this is a hope. So I would say this is one hope. This is our hope 1, which Sapphire didn't look, and this is our hope 2, which directly comes from the VC dimension. And so, and I took decision stumps. You can take any random forest also and go on doing classifying it with a little bit of randomization and till overfitting. And this will be your one of the hypotheses. It can also be applied here. It can also be applied to neural networks. You can take, just randomize it, take a different hypothesis of neural networks, right? Because ultimately neural networks, if you go for one perceptron, it's a linear separable classification. So it may be weak. So depending on whatever you take, since stumps is easier to explain, that's why I took stumps as an algorithm. But whichever you can take, you will get the same answer. So that's what the AdaBoost all about. And to formally answer your question about why this exponential loss, one thing is that it converges faster. You are absolutely right in that sense. It converges faster. And it converges exponentially faster, number one. Number two, this Rob Sapphire, as I told, that he explored in many other functions. This does not overfit. If we take exponential loss and try to fit it, it does not overfit. Though it's a practical result, and as I said, it's still open problem to prove formally that this kind of AdaBoost will not overfit in exponential loss. People have experimentally shown it converges very fast without any overfitting, but there is no such proof that it generalizes well without any overfit. The third thing that he got is with this exponential loss function is that you see this matter, that it simplifies your computation very much. If you do not take an exponential, as you can see, your computation gradually will be, since you take a differentiation and all those terms will again come up and all this, then your convergence and your computation both will be very much, very time consuming. So computationally, this is faster. So all of these three actually makes AdaBoost a very practical algorithm, and you will see it is being applied everywhere, including the Netflix prize competition. The top entry uses ensemble techniques to ensemble the movie ratings. Okay, so that is the top winning technique. And if you see the list, there is in top or second top, the name of the user and the name of the algorithm, they gave it something like ensemble, some with referring to ensemble. So that's an ensemble algorithm that they use. So this is one thing that I would like to like you to read through and also do it in practical points. You take x1, y1, this kind of practical examples. And as you know, each of them has weight 1 by n to start off with. Then what you do, you pick up, get first hypothesis, a weak classification hypothesis. You can use decision stumps as well. Then secondly, you see that which are the points that this hypothesis classifies correctly and which are the points that this hypothesis classifies wrongly. Then your next job is to update the weights at t+1 to these hypotheses which are classified correctly to reduce it. As you can easily understand, it is e to the power minus alpha t wit by z. So obviously it will get reduced here. On the other hand, your job is to increase the weights of this in wt+1, and essentially you got this one because you know that you are doing it this way. And then all of these are, since all of these are done with a choice of alpha which minimizes the error, which is 1 minus epsilon t by epsilon t, where epsilon is the wrong data point weight sum. Then after this boosting of the points, this is the boosting part, adaptively boosting, you get another data set D2, pick up another data set D2 with boosting, get next hypothesis H2 and proceed so on. Finally, you get a final hypothesis HTX, where T is the number of decision stumps or your algorithm that you use as a weak learning algorithm. Then you ensemble it. Ensemble is nothing, as you know, it's taking a sign of the sum of I equal to 1 to t alpha I hi x, and you proceed with this as your final hypothesis. That's the ensembling technique. Any questions?
Sir, can you please explain the third point, computationally faster again? I cannot
Oh,
understand it
computationally
properly.
faster means, see, finally what we get here is that, see, we are drastically reducing the equations in such a way that if you plug in this, it is nothing but wi by 2 if you take a sum. Otherwise also for individual
Yes,
ith point, if you plug in this one, this is wi by 2 into 1 minus epsilon by t.
Hmm.
Isn't it very
Hmm.
neat? Wit by 2 1 minus epsilon by t. So it's computationally very good. The
Oh,
computationally
this is the computationally faster thing. Okay. Then I got it.
yeah, because you have to only do a division, right, and a subtraction. Now, if you take any other thing, since we can take a log linear model, make it linear. When you take a log, it's a log linear model, and then we could separate. And that's why it is much faster than any other functions you will take. This computation of after derivative, if you try to minimize, it will grow. So that is one thing that they use computationally faster. But the other point of computationally faster also comes from this factor where they know that the amount of exaggeration they should make on the wrong points will sum up to half. That's a
Yes.
very neat observation. So all this points out to make it very amenable, and also experiment shows that it is very fast converging. So converging is the most critical criteria here. So, and also it doesn't overfit. That's a very practical observation. And most of the complicated data sets you apply machine learning algorithms, two things people definitely apply. One is people apply regularization that I said, because the machine learning expert and the general expert is only differentiated by its regularization factor. And the second thing that people obviously apply is they try on ensemble technique, and in ensemble, AdaBoost is the de facto technique. Okay, so the first name is two people do it. I think Freud or something, and then other is Rob Sapphire. Sapphire spelling is Chapire, I think. These are the two people who in 1997 brought this concept, which in 1999 was, I mean, absolutely the standard ensemble technique for machine learning. Okay, and they win the Gödel Prize in 2003, I think. So that's all for the ensemble learning technique. I just have a 5 minutes of time, so I just give a snapshot of tomorrow's class that I will try to do is. So all these are belonging to the additional topics that I will start, that I somehow I do not cover it in details, because when we are gradually learning the algorithms, supervised algorithms and all, I mean, we get ample matured to get this one, then it will be easily doable. And other thing why I do not introduce such additional topics, because many of the algorithms from these topics I will line up and prove that, for example, radial basis can be used in support vector machines, can be used in any kernel methods, can be used in clustering, can be used in your k-means k-nearest neighbor algorithm as well. So all these. So before that, before radial basis, something we will try to do, which is called dimensionality reduction, which is also a skill set in machine learning techniques. So as I said, that any machine learning expert should know some things. This is the third thing that machine learning experts should know. So he should know regularization, obviously, to make your algorithm better. In ensemble technique, he must have to use AdaBoost. Otherwise, this is the de facto ensemble. The other thing is that he should reduce dimensionality, because dimensionality is a curse. If you remember our k-means algorithm and all, everywhere d is a factor. It's a d to the power k something. It comes in your computation, right? The number of dimensions you are given with the points. So your dimensionality is a problem, because if you compute distance, 3-dimension comes in, takes you more. If you compute Euclidean distance, the more time to compute that. Instead of 2-dimension, if you go to 3-dimension, more, 4-dimension higher. So a particular attribute increases and your computation goes exponentially high with respect to that attribute. So what are the techniques to reduce the dimensionality? One of the things, as I said, the common sense wise, what we will try to do, suppose let us, so in case of classification, so suppose I have this kind of classification data, and I have also some minus. So as you can say that we have seen a linear classification and all, because linear classification, so this line is obviously W1 x1 plus W2 x2. That means I go for 2 dimension. Obviously, I have to compute 2 weights for both dimensions. So what if I'm showing it in 2 dimensions, but usually we do it for 1,000 or million dimensions and we reduce it. What if we could project these data points into 1 dimension? As you can see, if I project this into these dimensions, I could not separate it. The projection will be between these and this. I could not separate them well. Whereas if I project it in this dimension, there will be a cluster which is minus, there will be a cluster which is plus. I could separate it even in this dimension as well. Agreed? So therefore, you have seen something which is called kernel method, which enhances the dimensionality, right? In kernel method, what we do, suppose some data are non-separable in terms of line. So in kernel methods, this is the separation line. We take it in 3 dimensions and put it like this so that by a plane, we could separate it, right? We have seen that. So kernel method is kind of a dimensionality enhancement, putting it a linear boundary and then giving it back. It's in phi and then we do a phi inverse. Agreed?
Yes, sir.
Here in dimensionality reduction, we will follow the reverse path because we often believe that not all the attributes are always catering towards a separation factor. Not all the attributes at a time together matters if you can separate using a linear boundary. So this is the phenomenon of doing dimensionality reduction. So now you need to see where it gets scattered more. Some index, not a scattered index, but some index to show that the distribution can be separable, not like this one. I would not prefer to put it in x2 dimension only. I would prefer to put it in x1. So which among the x1 to xd number of attributes, we will see that which of the less number of attributes we will put in, so that this efficiently classifies the data with respect to these attributes only. That's the whole topic of dimensionality reduction. So the way to go in the next class, we will first define the metric of separation, as in this case. We will try to see that how features or attributes to be chosen. And depending on that, there is a very nice concept which is computationally very efficient, which is called principal component analysis, which is a statistical technique. We will see these 3 methods in tomorrow's class. And then we will also come back to our old thought about kernel and try to derive certain analogy of dimensionality reduction towards dimensionality enhancement. And then we will see sometimes kernel can increase the dimensionality to infinity as well, I mean, which doesn't seems, I mean, which you may thought about that generalization and all will be haywire, but it's a kernel, it's a function. You can define from the set of finite dimension, you can go to infinite dimension, if that makes your life to be separating to be more simplified. So we will see these 2 factors, which I believe are additional topics. One is this and one is this in the next class. Kernel methods, which enhances the dimensionality to separate, and the principal component analysis and others, which reduces the dimensionality to make your machine learning algorithms more implementable. Okay, so let us stop here, and with that we will start the next class. Any questions you can answer?
Sir,
Hmm.
sir, when we are choosing exponential function, it doesn't matter whether we take e to the power minus something or 10 to the power minus something, as long as it is exponential, right?
Yes, it doesn't matter. Yeah, but usually you will see the logistic functions. You can even choose a hyperbolic one, right?
Yes, sir.
So the thing is that you need to exponentially decay. Yeah, you are absolutely right. Instead of e, we can choose a 10 to the power. Then instead of ln, we will have a log base of 10.
Log to
That's
the
it.
base 10.
Base of 10.
Yes,
That's
sir.
it. I mean, it doesn't matter much since you are going into a logarithmic scale. So people choose e because it looks convenient to have ln in the equation. Even you can choose 2 to the power, no issue.
Yes, sir.
But I urge you, because this is such a nice method, I urge you to take an example and just go hand by hand. How does it converging so fast? If you see 3-4 points and see the error, it will converge in just 2-3 iterations. With 100 point, it converges within, let's say, 20 iterations or so. It converges very fast. That's the major thing that exponential decay brings in. Any other questions? Okay, so this AdaBoost, you can read it for any standard textbook it has. Internet is full of these sources, but I urge you to do these expressions, computations by your own hand, and then also take an example to do it. Okay. Thank you. That's all.
Yes, sir. Sir, one thing, if we assume 2 instead of e and go on, then it is it then take longer time to convert?
No. I mean, the longer time you will might not find it, because see here, instead of ln, you will do a log base. In the base, it will be 2. That's it. I mean,
Obviously,
until
they
and unless you are
cancel.
in the
Okay.
until and unless you are in the logarithmic boundary, your convergence is very fast, right? That's the major key of taking an exponential function. If you in log base 10, you might be more faster, but that see, everything has a price, right? This is a technique which will also have an impact on generalization. I am not going into the details of calculating the generalization bound, but depending on this value, your generalization will also hamper, right? So they got a trade-off and saw that E2, these are good factors to go with it, not instead of 10.
Okay.
Sir, so but in the final expression, log is not basically playing any role. Like everything is either inside square root or divide and multiply. There is no exponential term, no log term. So whether we take
no, it is not playing a role because you assume your error to be like this. Nah, your error may not be like this in the other case. If you assume square error, it will be different. Your alpha will be different. Depending on the alpha, if you see this expression, this one, depending on the alpha and all, if I substitute, it gets like this. Right? See, the convergence is not you do not mix the convergence with the computation. If you take instead of e, if you take 10 or if you take 2, this number of computations will be same. That I understand, because this thing will cancel. As you said, it is ln 10 doesn't matter. I will substitute it, it will cancel. Convergence is with respect to wt I plus t plus 1. With respect to wt, what you are choosing the next set of weights, that dictates how well you are converging, and also it dictates that whether how well you are generalizing. See, what is these weights? These weights are the representative points that is getting misclassified. If you put on too much weight, if instead of e, if you put 100, that means you are penalizing the misclassified point too much, and you are giving the correct points too much boosting. Right? Yes or no?
So I'm a little bit confused here. Like we are to update the weights, we are using the third equation, right? Where root of epsilon t upon 1 minus epsilon t is written. Or
Yes.
are we using the first equation?
No. We will use this equation. That is not for sure. See, this epsilon t is this one. I assume this one as my epsilon t, right? And when I computed my this one, it is the contribution of the weight with an expected loss. Then I got this. Now, if you have to change this E to some other condition, then all of these computations will change, and therefore this will not be so much straightforward as you look here, because the loss computation I make it equally looking to my weight updation. See, your only confusion is instead of E you can put anything. Instead of E, yes, you can put anything. But what I am saying is that
Yes, sir.
then you need to uniformly make this change also to this error sum, where I purposefully took that exponential loss will be a weighted exponential loss is my error. If
So let's
in
suppose
both,
we can do that. Let's suppose instead of E, we are taking 10 everywhere
you can
in the
take 10
previous
everywhere.
equation.
That's what I said. Then it will not change. Then it will
Yes,
not
sir.
change. Yeah.
So, sir, it doesn't matter whether we take E or 10 or 100 in all the equations, right? But as long as it is uniform in all the equations.
As long as it is uniform in all the equations. But usually what Sapphire showed that this is a good option. See, what does it matter if you take it 100? You are penalizing higher weights, I mean, misclassified points more, and you are boosting positive points more. There is not a fine line in between, right? E is more finer than 100. I'm not talking about the final equation. I'm talking about the philosophy, what you are going with it.
Yes, sir.
Yes. Okay. So if that is the case, if this penalization reflects in your loss function, that's why if this penalization reflects similar way in your loss function, that's why in the weight, finally, you are not seeing that E.
Yes, sir.
Usually,
Yes, sir.
that reflection of this penalization in the error is too much. E is more subtle.
Yes,
E is
yes.
more subtle in terms of loss computation. 100 is too much asking for penalty. You are correct that if you ask 100 here, your final answer will never change. Right? Your final answer will never change. That I understand, but your loss will not be practical in that case. Your loss is more practical looking this.
Yes.
Sir, did they try for different values? For example, E or 10 or 2?
You read that paper, you also may try using a Python script. I mean, it's in the scikit library, it is there. You can just try out with different values.
Yes, sir.
They had so I cannot cover this. It's a terribly big proof. They had a generalization impact on this. If instead of this, see, this loss will contribute in your generalization because generalization is the E out minus E in. Agreed?
Yes,
Yes,
sir.
sir.
So this E in will now sacrifice if you put 100 instead of E. That means this has an impact on the generalization, obviously.
Yes. Yes, yes, yes.
So that is why they should choose such a function which doesn't overfit, generalizes well, converges correctly, and all that, computationally easy. So they found E to be most suitable. I mean, you can say 3 is okay for it. I mean, as long as it is close to E. But as you said, if you take 100, your generalization will be very poor. Still confused?
No, no, not now.
Okay. Yeah. Any more questions? Swas, you want to ask something?
Sir, but did they give any mathematical proof like where they should stop?
Absolutely bitten. No. Yeah, absolutely. It was bitten to I mean to death by now. There are lots of
Sir.
papers. What is best? What should be? And there are still open problems about why it doesn't overfit and all that. Which functions will be least overfitting? And I would say this is a decade of research after 1999. There is a decade of research on AdaBoost. There is a book they wrote on AdaBoost, only with AdaBoost. It's called boosting, I think, adaptive boosting or adaptive boosting of machine learning algorithms and so on, from MIT.
Yes, sir.
Okay, but philosophically, this is what we do. I can understand there will be very many unanswered questions, but I see with a limited scope. I mean, if you go with the advanced machine learning course, some of these generalization bounds will be derived with the AdaBoost. If you are interested, I can point you that you can read Understanding of Machine Learning book by Simon David. There is a chapter called AdaBoost, which has theoretical proofs of these generalizations and the number of samples needed for having a pack bound and all that. All the theoretical questions that you are asking. But intuitively, this E-in has a sacrifice on the generalization behavior as well. So until and unless you keep this E-in to be in a feasible limit, you do not see E-out, right? You do not know how E-out behaves. But if your E-in is very weird, then E-out and E-in gap will be very weird. And with changing
Yes,
E, you change your E-ins. That's the point. Okay. I hope no more big questions, so we can close today's session. Sorry for being 10 to 12 minutes late.